focusing on MIPI CSI-2 camera security specifications for automotive. I'd like to turn over to Rick. Rick Wiefeld is the Senior Director of Technology at Qualcomm. More importantly today, Rick is the co-chair of the MIPI Security Working Group, the group that has developed the CSI-2 camera cybersecurity specifications. So yeah, Rick, over to you.
Okay, thanks, Ian. All right, so this this presentation is actually fairly timely. The first of a series of MIPI security specs are now complete in the adoption. Others are in the adoption phase. So we're getting to a point now where it's pretty clear from the work group members that implementations are ongoing. So I think at this point, you know, we can view the kind of the specifications as kind of closing down, or at least the first wave of the specifications kind of completing and implementations beginning. So let's get started. We're going to start with an introduction. Essentially, trying to identify what the security framework is all about. This is with regards to the CSI-2 protocol and the security associated with it. We wanted to spend some time looking at the flexibility that the security framework allows, and then move quickly to what we're calling profiling. We're going to look at the various options that the spec allows, and then certain profiles that are likely anticipated to be kind of within the first wave of implementations. And then we'll talk a little bit about security and functional safety operations when the two of them exist in a system. And then we'll conclude and move on to some questions. So in terms of the introduction, so cameras in cars, you know, the paradigm is that you have a number of cameras. Upcoming OEM requirements have up to 20 to 30 or more CSI-2 based sensors in a car, all of which feed in some fashion or another a centralized SoC. These are CSI-2 sensors. Sensors can include cameras, LiDAR, radars. All of these can use and often do use CSI-2 protocol. So this really has to do with protecting the data on, you know, en route from the various sensors around the car, you know, to the central SoC. The specifications have been in development for a number of years now. The work started in earnest in 2019 and are now completing this year. One of the things that we wanted to try and identify is that, you know, along the way, you know, we've identified the security work group has identified a particular checklist in terms of kind of the roadmap of how the, you know, the security framework has progressed. So we'll go through this particular checklist. Kind of big picture, not going to go into a lot of detail, but essentially the security framework is identified as in kind of three vectors. One is the so-called 1 to 5 model, and we'll talk a little bit about this, but essentially it's the chips along the way from the source to the sink. So the controller is identified as number 1, the target or the sensor is identified as number 5, intermediate bridge chips and things which kind of translate a very local interface at the sensor or the SoC to a long reach interface that needs to transfer data over 10 meters or so. Those are the intermediate components. So we have these 1 to 5 labeled 1 to 5 components within the model. And then we also have ABC. Think of that as a vertical stack in some sense, the ABC levels. The level A is at the bottom. You can view this as kind of hardware or silicon. This is what actually encrypts or data protects the, you know, the CSI-2 data. And then moving up the stack, there is a management layer, which we call level B, System Security Management, or SSM. And then at the very top, we have a level C, which is essentially the provisioning of the security credentials into the various chips. The details are shown. If there are questions, we can certainly come back to it. And then on the right-hand side, we have the 0 to 3 identified, which are essentially operating steps. So because this is a you know, a new paradigm for security, especially security in cars. We wanted to very explicitly identify kind of a set of reference steps where we're starting at 0 at the top right. With the OEM or the tier 1 would provision authentication credentials into the various chips. Then there would be, in some sense, on boot, there would be an authentication and a secure session establishment. And then after that's complete, essentially it gets down to the hardware where data encryption and integrity operations proceed. So this framework was identified to be as explicit as possible to kind of build understanding and kind of operating principles. So in terms of looking at the CSI-2 stack, so the CSI-2 forms the basis of this security mechanism. The supporting materials for these specifications are built into 4 different specs. One is a MIPI security spec. One is a MIPI security profile spec. One is the detailed implementation of that for CSI-2. We refer to that as the camera or CSI-2 service extensions. And then we have a command and control interface, which is essentially I2C. So you can see here that the security layer occurs in the stack above the CSI-2 layer. So what we refer to it as being essentially at the application layer, if you're thinking of an OSI stack kind of perspective. And you can see that as you progress down, you'll see this particular example showing the security CSI-2 secured data being transferred over the MIPI A-PHY for a long reach connection, and then over a C-PHY or a D-PHY in a short range mode. Now, the interesting thing is that even though it's shown as transmitting over C-PHY, D-PHY, or A-PHY, the security mechanisms occur at the protocol layer, so they're really independent or oblivious to the actual transport underneath. And again, many of these specs are now in the adoption phase to be completed soon. And the last one, the CCI service extension, is expected to complete in the later part of this year. Okay, so this is the checklist. One of the things, and this was something that took quite some time to kind of evolve towards, but at a high level, what we're talking about are the kind of the 2 bookends. We on the left side, we need to figure out what are we trying to, what are the security objectives, and then on the right hand side is essentially, the mandate to really use industry standard cryptographic principles, so the NIST standards and things like that. So along the way, in between the bookends, the first objective was to understand what are the security goals. Do we want to encrypt the data? Do we want to integrity protect the data? Do we authenticate components? The answer is, in certain cases, yes, yes, and yes. Very importantly, we wanted to understand the extent. Extent is essentially something where you ask, on what granularity do you want the data protected? Do you want it protected on a per hop basis? Do you want it end-to-end protected? Do you want it protected at the link layer? Or do you want it protected at the application layer? And we'll go into the paradigm that MIPI ultimately chose. And then if you're looking at end-to-end and application-based security, then we wanted to understand these are 2 new aspects of CSI-2 security. There's an aspect of source selective security. In other words, do you want to protect certain portions of a CSI-2 data set more than others? And then there's the notion of partial integrity support, where you may choose to configure the security mechanism to only provide protection for part of the data. And then finally, the last step is if you wanted to do authentication, which is a norm. Essentially, you want to understand what is the security handshake protocol. It turns out that MIPI Security ended up using DMTF's SPDM spec. Another option was, of course, the TLS mechanism, which was ultimately rejected in the first wave. And then importantly, do you want to have authentication be 1-way or 2-way? So we're going to walk through some of these aspects. So what are the security threats? Well, the very first one was we wanted to protect against unauthorized components, and you do this typically via an authentication step. So this essentially establishes trust between the sensor and the SoC. And it can be one way or two way. By two way is meant that if you have a sensor that's retrofitted into a car, you want to make sure that the sensor is somewhat analogous to the printer cartridge paradigm. You want to make sure that the printer cartridge, or in this case, the camera sensor, is authentic. By the same token, if you want to execute two-way authentication, then you want to make sure that the SoC, or the central controller, is authentic from the perspective of the sensor. And the way authentication works is these are provided by authentication credentials, and it's either certificates or pre-shared keys. The second thread is to identify when data in transit from the sensor to the SoC has been modified. And essentially integrity protection is what ensures data is unaltered in the transmission from the sensor to the SoC. And this is provided by the message authentication code, or MAC. And the third one is compromising data privacy. Certain data may be deemed to be um, to need to be maintained as private, and in that case, you encrypt the data. And these three kind of mechanisms are, relatively well understood in the security world. MIPI has elected to make some tweaks on it, and we'll talk a little bit about that. So the security extent, this is one of those, in some sense, one of the tweaks on security mechanisms that are well known in automotive. So different standards, provide different ways of securing the data. Um, and in particular at what protocol layer and from which starting point to which ending point. So we can talk about distinguishing a per hop based security mechanism versus an end-to-end one. You can talk about distinguishing, do you want security at the link layer or the application layer? And if you look in the diagram on the right hand side, you can see the 1 to 5 model components, the source and the sink. The red line illustrates the pixel data that's sourced by the sensor and sunk by the SoC, and you want to protect that data. Um, Different standards you can see on the lower right hand. You can have some implementations that are particularly using Ethernet MACsec, for example, or HTTP. They essentially generally protect on a hop-to-hop basis at the link layer. In the lower corner, you see an end-to-end or application layer kind of perspective. And that's, very much like a TLS browser client application, talking to a web server. That's essentially a TLS end-to-end at the application layer kind of mechanism. And MIPI is opted for this paradigm. One of the reasons for adopting it in that fashion is it provides certain advantages. One of which is it becomes independent of the link layer underneath it. So whether it uses MIPI A-PHY or whether in the future it uses Ethernet, these are all kind of independent of the CSI-2 based security. And the second item is that it does allow, this kind of paradigm does allow a couple new features, one of which is called source selectivity. Certain parts of the frame can be protected more than others, and then partial integrity, which is a variation on that. So we'll introduce that in the upcoming slides. So here we go. So source selectivity. So CSI2 security, one of the main things that we wanted to try and include is the ability to protect more important data with higher security. Depending on the use case, it may be that you want to, protect the pixel data more than let's say, the metadata. In other cases, you may want to, protect the metadata higher than with a higher level of integrity than the pixel data. So these kinds of choices are made available in the configuration of security. So this ability to kind of have different levels of relative security level is captured in what MIPI calls the security variant. And you can see that in the figure on the right, there is kind of a decreasing from left to right, the opportunity to decrease the level of security from case one or two, which is full integrity, with or without encryption, all the way down to no integrity. The cases of interest are actually the so-called SV3 and 4 in the middle, where you can essentially, and you can see in the bottom of the graph, the blue areas are what identifies the level of data protection. You can see that on the left cases, everything is blue, meaning all the data is protected. And then in the middle, you can see that only certain portions of the data are integrity protected. So this is what we mean by the the ability to identify different levels of protection, different SVs, if you like, and apply different security to different portions of the video frame. One of the items is, of course, the security handshake. There's the choice between one-way and two-way authentication. Both of these are available within the security mechanism. MIPI leverages this SPDM security handshake, which is very closely analogous to TLS. And MIPI does support both one-way and two-way or mutual device authentication. And you can see that this ABC layered model is in place. Level A on the bottom is if you like, the hardware or the silicon, where the integrity and the encryption is applied. The software suite in the middle sets up the handshake and configures each of the devices for the various security options. And then top level is level C, which is essentially the provisioning. So the security handshake was a major decision by the security work group to understand, which kind of high level, security handshake paradigm was of interest. So we're going to talk two aspects about the security flexibility. The first one is the topology. So we identified before the 1 to 5 reference model these 5 reference components. The controller and the sensor are the 1 to 5, and then these intermediate components. Now, the bridges need not exist as explicit chips. The long reach functionality can be built into the controller or the sensor. Typically, in the first wave of implementations, there'll be separate bridge chips. And then, very importantly, security is nominally only implemented in the 2 endpoints. However, in the bottom portion of the screen, you can see that the security framework does allow different kind of architectures where the security could be implemented in the bridges. Typically, though, the security are only in the 2 endpoints. So that's the kind of end-to-end reference. This is a different view of the topology. In some cases, you may see clouds that connect the source to the sink, the sensor to the controller. And one of the key aspects, as I mentioned earlier, is that the CSE security is independent of the cloud, whether it's Ethernet, whether it's A5, and that sort of thing. The security is tied from end to end and also at the application layer. The second aspect of flexibility is the security context. So before we get into some of the details, let's start by looking at the frame anatomy. So this is a typical CSI-2 frame. It's been in play for 15 or so years. It's used in every smartphone. It's used in many of the cars today. You can see that the frame is composed of these so-called frame partitions, these so-called FP1 through FP5. These are names that the security folks labeled, in a new way. CSI2 doesn't refer to these. These are just names that the security folks needed to apply to CSI2 partitions of a frame in order to be able to selectively apply different security to different frame partition. So this is a representation of a CSI2 frame according to one virtual channel. And again, these FP1 and FP5 are kind of the bookends. And then the intermediate, you can have any combination of FP2, 3, and 4. Pixel data is, of course, as defined in FP3. We sometimes refer to these as top block, middle block, and bottom block. So this is very much a representation that we're able to subdivide the frame into different specific um, parts so that you can apply security differently for each of these different parts or partitions. The four paradigms in which security can be, independently configured are as follows. One is the protocol. It turns out there are two security protocols. One is known as FSED, or a frame-based service extension. The other is a SEP, or a different way of applying security on a more granular level. We'll talk about that. There's the notion of tag mode, in which you're now able within the framework to compute the MAC on different levels, whether it's on a per packet basis or whether it's on a per frame basis. So we refer to that as the tag mode. The security variant is something that was introduced earlier, which is essentially the level at which you want to protect the data, whether it's protecting every single message within the frame or whether it's protecting, let's say, every other line of the video frame, things like that. And then so the different security levels involve the idea of having partial integrity applied. Those blue stripes, whether it's every other line or every other column in one of the previous slides. And then Cipher Suite, there are two options. One is a high performance mode and the other is a more efficiency mode. So we'll refer to these as kind of the four vectors in the security context. This tries to identify the protocol. You can see that essentially we're assuming that it's an end-to-end security paradigm. In other words, the security is initiated in the sensor and terminated in the SoC and the controller. There are these two different protocols, FSED or SEP, that protect the data plane. And we also have the command and control service extension, which protect the control plane. You can view that as essentially I2C security. Even though it's not emphasized in this presentation, the security mechanisms are in many ways running alongside of the functional safety mechanisms in the data transmission. And essentially they're able to operate concurrently. So these are the two, these are essentially the data plane and the control plane security mechanisms, and they're configured independently, and you may want to apply different security methods to the data plane or the control plane, again, depending on the use case. So this gives a representation of the different security protocols, whether it's FSED, a frame-based, or whether it's the more granular SEP-based mechanism. You can see in the first column, you have basically an old-fashioned CSI-2 frame with no security. So you can see the frame start and frame end kind of bookends. You have the embedded data before and after the pixel data. Now, what happens in the FSED is where you have three new CSI2 messages which are inserted into the data stream. And essentially, these are mechanisms where there are MACs or media or message authentication codes inserted in the various parts of the frame in order to kind of identify the data protection for those components of a frame. On the right hand, and those are the three orange CSI, those three colored CSI2 messages, the FSED control sync, top tag, and frame tag. Essentially, these are frame-based. Contrast on the right-hand side where you have, in the case of SEP, where it's possible that every single CSI2 message in the frame is independently protected. So you can see that the SEP one is more granular in the use case where you need to protect every single message. SEP may be more appropriate if you're looking at a less granular frame-based approach, then FSED is an option. The reason that both of them were identified is essentially, part of the security paradigm of being flexible. SEP and FSED are both available. A sensor may support one or the other at a given time. The controllers typically would need to support both depending on what the capabilities are of the various sensors. This is a different view of the different protocols, the FSET or SEP. You can see on the top row here we have legacy CSI-2 packets without safety and security additions. The FSET protocol inserts these 3 orange packets along the timeline of the frame. And then in the SEP protocol, every single CSI-2 message is separately protected. So these are 2 of the major options in the security paradigm. Second one is tag modes. So you can see here that again, a tag in this context is defined as either a security MAC, but it may also include functional safety elements like a CRC or message counter, things of that nature. The tag mode essentially identifies when the tag is sent within a particular frame and which packets are covered by that particular tag. The tag mode is configured by the SOC. There's, in some sense, a discovery mechanisms at the beginning of operations where the sensor will identify its capabilities, and then the SOC will configure, the ones that are appropriate for that use case. You can see that in the FSET case, in the center, in the middle column, you have those 3 additional packets which are sent, whereas in the SEP case, you can see that the MAC, the blue MAC boxes are identified in different tag modes. In the limit, you have 1 MAC for every single message, but there are different options available for the SEP, for the different SEP tag modes. We've seen this diagram before, the security variant. You can see that in terms of the integrity protection shown in blue, the framework allows for different levels of data protection based on the the paradigm. The one of the reasons for doing this is that sensors can become hot, the processors can become warm. Essentially, this framework does allow you to kind of back off the security in order to relieve kind of some heat pressure and things of that nature. So it does allow additional kind of degrees of freedom in the operations. The security variant versus frame partition, part of the flexibility is that you can see, again, based on the different frame partitions, you can configure different security variants separately for each of the frame partitions. So again, this is a representation of the different flexibility options that the framework does allow. The Again, the basic argument for this is to provide flexibility, based on operating conditions in real time, um, to allow, operations to run, smoother depending on the various operating conditions. The Cypher suite, there are performance algorithms, there are efficiency algorithms. Essentially, kind of the breakpoint between the 2 of them is typically, depending on the sensor data rate, anywhere from 1 to 3 gigabits per second may be just fine with running things according to efficiency algorithms. Above there, they're typically run for things at 4 or 8 megapixel cameras. They would typically run in performance mode. Both of these algorithms, um, whether it's CMAC or GMAC, with or without encryption, support 128 and 256-bit keys. The first wave of implementations may end up using 128-bit keys. And again, the SOC controls which of these cipher suites are applied, for a given sensor, throughout the system. Now, we've talked a lot about the flexibility. A very concrete exercise was undertaken within the security work group to profile some of these options, to give them names so that you can kind of promote interoperability among the various options. So we'll take a look. So again, the CSE, the camera service extensions for security, it's very general purpose with many options. The first use case is automotive ADAS, of course. And the work group took two specific profiling steps. One was to profile the security handshake, the various SPDM commands, and the other is to profile specific features and give them names so that they could be very easily identified. The SPDM is very much like TLS. If you're familiar with TLS, essentially it's a command response kind of system. The controller will essentially issue commands, the sensor will respond. There are a number of very explicit commands within the within the framework, whether the flow is certificate based or pre-shared key based. Um, every command has a set of different parameters. We needed to identify which of those parameters are useful or are needed for CSI2 security, and all of those were profiled. We came up with 4 SPDM profiles. We refer to these as SPDM profile 1, profile 2, 3, and 4. And you can see that in the table, there are a number of kind of key distinguishing factors, whether it's certificate or pre-shared key based, whether it's one-way or two-way authentication, and that sort of thing. All of these profiles have a security level of 128 bits. So for each of these SPDM profiles, each SPDM command is very explicitly profiled for interoperability. 256-bit operation is available, and over time, we will very likely end up identifying more profiles based on how the CSI2 security is actually being used in different markets, not only in automotive. The security profiling is quite a daunting challenge. On the left, you can see what we refer to as the security landscape, and you can see that there are different tag modes, there are different frame partitions identified, FP1 down to FP5. You can see that there are different options available in different tag modes, and essentially the left-hand side of this is essentially a landscape. In other words, identifying which features are available um, within the specification, and most of these are shown as optional. There are some that are shown as mandatory because they're absolutely required. And you can see on the right-hand side the identification of particular profiles. And MIPI's identified eight security profiles, so-called CSE Profile 1 through CSE Profile 8. And again, these are kind of a very concrete set of um, most likely um, configurations of these parameters that the security workgroup members have determined. This is not to say that you can't cherry pick and define, an OEM or a tier one can identify a particular new profile. This is just to give names to very concrete profiles for the purpose of, identifying a starting point in many ways. So we've gone through a lot of details. In summary, the MIPI spent the last 3 or 4 years within essentially the camera work group and the security work group to finalize a number of kind of first wave specifications. The CSE spec, the camera service extension spec, is adopted. The other two are to be adopted very shortly. The fourth one is the command and control service extension that we expect to be complete later this year. MIPI security is very different from two perspectives. One is the ability for identifying source selectivity, meaning you can identify different levels of security protections for different parts of the frame. And furthermore, you can apply partial integrity, meaning even within a particular portion of a frame, you can choose to protect only some of the data some of the time. And then we've introduced this notion. I didn't focus on it a lot, but there's this notion of what we call end-to-end application-based security. End-to-end meaning from the initiation point sensor to the termination point SOC, but also at the application layer. So we refer to this as end-to-end with the important distinction that the actual security paradigm is independent of the underlying in-vehicle network. So CSI2 security works wherever CSI2 is used. With that, I believe that is the end. Ian, let me hand it back to you, and we can take some questions.
Yeah, thank you, Rick. Thank you for the presentation. MIPI security is based around use of SPDM as a method for authentication handshakes. May not be a method that too many people are familiar with. You may be familiar with, I guess, more the more common methods, TLS maybe. Why did MIPI choose to go with SPDM over other methods?
Right, right. So back in 2020, I think we started to explore the question of which handshake do we use. TLS was one of the first kind of candidates. SPDM was leveraged from TLS. It is developed within the DMTF organization. Um, Essentially, there were a couple of reasons why SPDM was chosen. One, it was based on TLS, um, but for a second reason, TLS doesn't have a lot of the um, kind of more system level details that an embedded system like a car requires. Um, so it didn't have many of the features that were desirable in cars and in embedded systems, of which a car is kind of imagined as emulating. Um, it was very flexible. It did allow, or it does allow, um, you know, the issues that we wanted to include, such as the partial integrity and source selective security. It does allow that very, very natively. Um, and it was a consensus of the work group that we wanted to reuse, a specification instead of developing one for MIPI itself. Um, one of the MIPI partner organizations that we work with, which is Visa, for display security and automotive. They also ended up choosing SPDM. So in many ways, there's kind of a good synergy between the camera and display groups,
Mhm.
across the industry.
Okay, thank you, Rick. I had a question come in on from the audience chat. I'll put it up on the screen here. How can I check that your solution is security compliant as far as automotive security is concerned? Is it ADAS approved?
So yeah, it's a fair question. In ultimately, and that's part of the reason why SPDM was selected, was that it was functionally a secure a secure solution. It was developed by experts within DMTF over many, many years. So it was, and it has gone through its various kind of, standards-based kind of security, checks. Um, Ultimately, of course, every security solution is in some ways implementation specific. MIPI does not, and many organizations do, some don't, have a more formal compliance program. MIPI does or is exploring this not only for security but for other portions of automotive specifications. So I think the short answer is that SPDM has been, pretty closely analyzed within the DMTF organization and including MIPI members. So it has a certain level of kind of familiarity and proof, within those analyses. Ultimately, there may be a desire within MIPI and the industry to kind of, come up with mechanisms to, um, you know, to, to better understand security from the perspective of testing methodologies.
Mhm.
I should say as well that many of the MIPI specs undergo following the specs development, go through a conformance testing phase where you'll be able to essentially apply tests, to the security mechanism. So that's something that's a work in progress, and we'll be looking at, for the remainder of this year.
Okay, thank you, Rick. Just to look at one of my questions. Again, it's a question that actually often gets asked. Some of the face-to-face presentations that we've done on security, and that's regarding whether credentials in the system can actually be shared. Obviously, the framework relies on potentially in an automotive system, lots of security credentials being used. And one question we say we have had previously is whether you can share credentials between different components.
So ultimately, the security framework doesn't preclude that. It's part of the out of scope level C, which is the provisioning aspect. Typically, though, and again, there's freedom there. So really, the ultimate decision is up to the builder, it's up to the OEM and its vendors. But the kind of the simple and most practical method is to apply independent credentials to every chip in the system. And then, based on those credentials, you undertake the handshake to identify, an authenticated connection and that sort of thing. So the framework does not preclude the ability to kind of share certain credentials. Many security folks would not recommend that. In some cases, such as a multicast, you may need to share credentials when you're sending data to more than one endpoint. And again, the framework allows this, but the kind of the typical paradigm is independent credentials in each component.
Okay, thanks, Rick. So just about a minute remaining. Perhaps it's a good question to ask about what the security working group is up to presently. Obviously, you've mentioned that CSE v2 is adopted. Other specifications are nearly complete. Perhaps you could just give us a flavour of what the security group will be doing over the next few months.
Right. So the first objective is to complete the command and control interface security. So that's in effect the I2C security and functional safety. That's in a very advanced stage. Over the next few months, that should be complete. And secondly, there's work just starting on a CTS, a conformance test specification, which is typical of MIPI specs. The basic idea there, and it relates to one of the questions about, how do you verify the security mechanisms in the MIPI spec. A CTS would typically go through a particular spec, in this case, the CSE spec, for example, and every shell statement will be identified with a particular test. So it's a very specific set of tests that a test vendor could apply to a particular system in order to kind of help verify it. So essentially the CCI SE command and control interface spec completion, and then working on conformance test suite specs for camera security.
Okay. Okay. Thank you, Rick. I think we're approaching time, so I have to thank you very much for your presentation today and giving us your time and answering these few questions. Rick, is there anything else you'd like to add before I just sort of close out today's session?
No, I don't think so. We certainly did want to thank all the MIPI members who've participated in this. It's kind of concluding on a 3 to 4 year exercise, and we do see implementations progressing. So I think it's we're off to a good start.
Great. Okay. Thank you. Okay, so just to wrap up for today, obviously plenty of ways to find out more. And if you're watching on demand, if you do have questions, we can take those via the admin@mipi.org email address. They were a small team at MIPI. Your email will come through to the team. It will get responded. You will get a response. We'll work with the subject matter experts to get those responses back to you. Obviously, there are white paper introductory guide to MAS is available on the website. It's a good introduction to the whole MIPI framework. It obviously includes the security component that Rick's just spoken about. If you do want to kind of stay in touch with MIPI news, we do have a dedicated automotive mailing list. It means you won't get spammed on every email from MIPI. You'll just get the ones relevant to the automotive world. So that wraps it up for today. Hopefully we'll see you tomorrow. Thanks once again, Rick, and we'll close out for today's session.
Bye.